Okay, hi everyone. We are going to be doing some working session work about metamathematics and its relation to our physics project. And we actually have a bunch of notebooks up on the screen because we were working on these just last night. And maybe I can explain a little bit about what's going on. What we're trying to do is make a minimal model for mathematics. And the essence of that minimal model is the idea that there are propositions, and these propositions are combined through various forms of entailment. And the primary type of thing for mathematics, we're trying to make a model that is sort of the minimal model, and we're thinking about when we do find equational proof, for example, that is full of substitution lemmas in which one proposition is sort of entangled with another proposition through an event to produce, in that case, a single proposition as output, at least in the theorem proving case, although a given type of entailment could have many possible outputs. But the place where we got is what we were looking at is this is an extremely minimal model for, I should probably make this bigger, shouldn't I? An extremely minimal model for an entailment where we're just saying you take two expressions here represented as just lists of zeros and ones, and the entailment simply consists of creating new expressions by joining things together like this. Okay, and then so this represents, in a sense, each one of these is a mathematical theorem, and these are ways to combine theorems to get new theorems. And then we also looked a little bit at the way of looking at the state of mathematics at a given moment, which is basically saying, let's see if we've got a good example here. Okay, so the state of mathematics here is like we've got these two sort of quotes axioms that we're starting with, and through entailments, that complete state that consists of a collection of propositions is transformed into this complete state. That's different from our token event graph, where we are representing events that are sort of at the more microscopic level, where it's just individual propositions being combined. Here we're taking the complete state of mathematics, represented by one of these boxes. That's sort of, actually this particular one, why doesn't this have all the known true theorems? Is this accumulating theorems or not? This one doesn't seem to be.
It's dropping them.
It's dropping them when. Okay, so I think we had another example here. Yes, this is our other example where we're simply accumulating. And by the way, what I think we're going to find when we actually look at the more realistic mathematics case is that it is going to be non-trivial to preserve the theorem. Just like if you think about physical space, preserving a particular atom of space is not something that happens most of the time. You have atoms of space that have sort of the same configurations, but you don't have the same atoms of space being preserved. That makes sense. And I think we're about to find the same thing. Okay, but so this is representing the evolution of mathematics. And each different path here represents a possible evolution of mathematics. And any given, so for example, two different researchers, so to speak, could be on different paths here, discovering different mathematics. And one feature probably is that there's probably causal invariance or some form of confluence here. That means that independent of what path you took, I think that's a necessary, well, certainly for this kind of entailment. Okay, so here's a question that we should start making questions here. Which entailments lead to causal invariance? Is that an obvious any thoughts, guys?
Is it obvious what?
Well, which kinds of entailments yield causal invariance? We gotta make entailments a spelling word.
Yeah.
Okay, which ones lead to causal invariance?
Right.
And that's the, e.g. substitution lemmas, critical pair lemmas. I don't know why we're calling them lemmas, because they're really not. They're really entailment. What should we be calling them? They're really entailments.
Well, that would be clearer. Yes, I felt the same way about the term lemma.
I mean, they make lemmas. Okay, so just a minute. So now we're talking about. Let's talk about. I think we're going to talk about. My current name for them is troughs, which are tree hypergraphs.
Yeah.
I'm not sure that's going to be a surviving name. But anyway, in the first question is, okay, so types of entailments. And so a given entailment, what is the right thing? Okay, an entailment is an event in our. By the way, did you have a chance to look at the inventory of possible entailments?
No.
Okay.
Well, we've looked into them. There are a bunch of them.
I know, but what's he say?
Definitely have no time to implement any.
Yeah, right. But are they? I mean, the question is, okay. So let's look at where do we have our list of entailments? Oh, here we go. There was a list of rules of inference here. Now, but let's just understand what. Okay, which one of these is a substitution? Is what we're calling the substitution entailment. Or are these of a different kind?
Oh, I suspect it's modus ponens.
Modus ponens, yeah.
Is it? See, the thing is that modus ponens, very confusingly, has this is an implication. Whoops, this is an implication. I'm so confused by all of this. But Kinji says on a live stream suggests the term paralemma, and I'm now about to find out what a paralemma is if it's a thing before. But that's an interesting name. I mean, really, is it a paralemma or a metalemma? Or is it a lemma at all?
It's more a rule, some kind of meta rule.
Yes. Well, I mean, we're calling them entailments. Yeah, well, that's what they're usually called, inference rule. So maybe that's what we should call them.
Yeah.
Yes.
I mean, the reason I don't like inference rules as such is because it seems to have a notion of implies, which is not good. But maybe inference rule is the right thing, and that's the way that mathematics progresses by inference rules as physics progresses by its kind of rewriting rules. Okay, let's go to troughs, which aren't going to survive as named troughs. But the idea is, so in this case, what we're doing is we're just saying, okay, so wait a second. So we've got, we talked before about possible models of, okay, so what we're looking for is models for tokens, basically. And, want a math-like model for a token.
Mm-hmm.
Okay? And the answer to what that should be is an expression. we think, and an expression. Now, the expression
it could be just a sequence.
Why isn't that itself an expression? I mean, so wait a minute. So then the question is special types of expressions. And whether this is the right way to think about it, I'm not sure. But one possibility is, ones with rules. I mean, in other words, okay, so what's in an expression? In an expression, there are variables and there are operators. Okay, so what we've done, in a sense, the human mathematics thing is introducing a bunch of operators. And one of those operators might be this operator, which then is something which can actually be used to represent a rule. Does that make any sense?
Yeah. Also constants. Variables.
Are those different? Are they different?
The operator is just the constants.
With arity 0. No,
Yeah.
maybe.
Yeah, I think so. Okay, so I'm going to claim that the thing that makes this not, okay, in the Rulial limit, we introduce all possible operators. But outside of the Rulial limit, we're throwing a particular set of operators that are kind of the somehow the material of our mathematical theory. Does that make sense to you guys? Because otherwise, yes, we got to start from something. It's a little different from physics, because in physics, okay, so the basic claim is, in physics, we're assuming that the structure of space-time is just pure hypergraphs.
Mm-hmm.
Now, in the end, that may not matter, because it may be in the Ruliad limit
mm-hmm.
that you could have anything there, but it's just a convenient model.
Mm-hmm.
You know, so I mean, in actually, this is really about more general things than troughs. We'll put troughs down below here. Okay, so yeah, so the claim here, which is actually an interesting claim, is that, you know, in the 30 years between sort of when I first started thinking about the physics project and when we actually got to do it, one of the big questions was, what should the data structure be?
Right.
Okay.
Yeah.
And you know, and actually, this is an interesting point, that the Ruliad doesn't care. And in a sense, what we're doing is the interpretation, we need Ruliad to be a spelling word.
Recognized, yeah.
Right. And Peter on our live stream is asking, can I get a Rulial space T-shirt yet? You know, that's a good idea too.
Yeah, but it only comes in extra large, I think.
Why?
because of the content constraints. There's no way we're going to get a medium-sized T-shirt for the Ruliad. It's very capacious.
I thought it was the transfinite XL. Okay, X infinity L. But we can reduce it in for three-dimensional space. It could get reduced somehow, perhaps. In any case, okay, but the basic point here is the ultimate data structure doesn't care in the same sense that, you know, we can use Turing machines, we can use register machines, whatever else. There's always a conversion. Now right. The question is, for math, because we want to, you know, we want to use a structure that looks like traditional math, so that we can do empirical metamathematics, for example. Because, in other words, you know, what this is like is saying, you know, if I'm going to represent some physical system, I want the right degrees of freedom to represent it. I could represent a pendulum in terms of the position of the end of the pendulum, or I can represent it in some bizarre, Lagrangian mechanics variables that are very derived, so we want to do something where we can actually do the empirical measurements. And therefore we need a data structure. It's sort of an interesting case. We want to invent a data structure that is empirically accessible, so to speak, as opposed to a quantity that's empirically accessible.
But at what point does the structure start to exhibit the properties of recognizable math?
Right. Well, okay. So my claim is we need to work from two ends. On this end, we've got things that are not recognizable math.
Right.
But they have certain properties.
Yeah.
And in the end, I don't think they're going to be, I think, and what Nick has already got here suggests this to be the case, that the more realistic math is going to look exactly the same. That there's not going to be a big difference, except that in the more realistic math, we're going to be able to pick it out and say, look, in actual math formalization systems, here's what happened.
You mean it looks exactly the same at the molecular, so to speak, level?
Yes.
Yes. Well, that's right. So at that scale, familiar mathematical, the math that's familiar to us, it's not recognizable. But if you generate it for more than just a few steps towards some limit, then it should begin to exhibit the properties that we see.
Okay, well, let's write this down here a little bit.
Yeah,
I mean, so at the quotes molecular scale, okay, the molecular scale is sort of axiomatic formalized mathematics. I think. I don't think you have to go any lower than that. I think. We'll see.
And this could be any kind of axiomatic system, a la NKS. Basically.
Yes, I think so.
Yeah,
I think so. I mean, these kinds of things. But the only thing that might be the only aspect that might go lower than usual, is that I think is to do with variable naming, which I suspect we're going to have to go.
Right.
In other words, this thing about what's a generated variable may end up being less human accessible, and things like whether the operators are the same operator or not, variable naming and operator persistence. Okay, because it's not obvious to me that the dot operator in one instance is going to be the same dot operator as in another instance. It could be that is essentially a reference frame. We shall see.
We shall see.
Okay, so then
probably positions too.
Say that again.
Because our inference rules act on in particular position. The substitution happens.
I see. Okay.
For example, if you decompose critical lemmas into each substitution that is made during the unification step, it also kind of goes lower.
Is that just an initial condition? Can we kind of describe it in that way?
Nick, I didn't say that again. I didn't. There was some words that got smooshed there. I didn't understand it. Can you say it again?
I said that during the critical pair lemma, deriving the critical pair lemma, there is a unification step, which is basically just a bunch of substitutions.
And
they are not made. They don't make sense individually. Right?
Oh. Okay, because there's some structure that has there's some positional aspect to the data structure. Okay, but anyway, so this is all right. Oh, I see what you're saying. What you're saying is, what in math, in doing math, one application of an inference rule is an atomic thing. Whereas what you're saying is, but we have the subparts of an inference rule application. Is that what you're saying?
Yeah.
It's interesting.
Okay, that is an interesting point.
Yeah.
Okay, so
but can it be thought of this structure, Nick? Can we think about it in terms of some sort of initial condition?
I'm not sure about what do you mean by initial condition. I would think of this like some kind of entangled substitutions.
Yeah, that's what I think too.
Okay.
Right. I think, but okay, so we've got two different scales. The next scale is the multi-way molecular scale, multi-way molecular structure. And the other thing is, continuum limit. Okay, so what is the multi-way molecular structure? So that means one of these kinds of things, or one of the token event graphs. Wow, what the heck is going on there? And what is the correspondence with mathematics? I mean, that is okay, at the token event graph level, a state of mathematics. Yeah, okay. In a token event graph, an instantaneous state of mathematics is some spoliation, is some slice, is some time slice that picks up a certain set of, this is not right. This is not right. Okay, I was going to say that picks up a certain set of propositions. Okay, this is not in fact correct, because this is the state, the instantaneous state of, quotes, all possible math is some time slice, because there are branchially different histories of mathematics, so to speak. Does this make any sense? So in the actual history of mathematics, one is progressing chunk down this path. One of these is the history of mathematics, at least as well. You see, this is where it gets a little tricky, because we've got different mathematical observers, right? This is the point. So it's a different observer.
It's like an observer history.
Yes. For a given mathematical observer, there is okay, this depends on the model of the mathematical observer. Okay, potentially. Okay, let's make a separate section here for mathematical observers. So the what can we call them? The narrowest observer follows a single path in the multi-way system. Okay, multi-way system whose rules are rules of inference. And whose states are complete states of mathematics, right? That have already been, okay, in the multi-way system, we've already done equivalencing from the relative to the token event graph, right? In other words, we've collected buckets of tokens and put them into states. Does that make sense?
Collected buckets of tokens and put them into states. Yeah. Okay.
Okay. So here, the narrowest mathematical observer follows a single path in the multi-way system. And
Single-minded observer.
Yeah, that's right.
The
narrowest single-minded observer.
So what's the caricature of this person? They're involved in some particular field. They don't necessarily find a connection to any other field, and they just make steady progress in that field.
That's not the thing is that they are on their desert island independently rederiving mathematics. And they didn't look at anybody else's proof of anything. So they are doing their math course, which is going to be a constructive math course, and they're going to prove everything, starting from, basic arithmetic or something, and going up to whatever they go up to.
I see. Okay.
Whereas a different path here is this is a person who uses textbook A, and this is a person who uses textbook B, right? So in other words, different paths are like building up math by with different textbooks.
But what do you mean by textbooks in this case, though?
Well, I mean, okay. So here's the point: that according to with confluence and or causal invariance, I think confluence is more directly relevant here. You know, they'll both be able to do the same horrible exam. Okay, but the intermediate theorems they proved are different. Do the same, I don't know what, do the same, well, whatever, exam computations, but the intermediate theorems proved were different.
But would you not say that this applies to larger fields of math, which at some point are separate, but then people find different connections between them?
Possibly. I mean, possibly. Look, the main point, but I think it can be done even at a much more microscopic level. You have one bucket of theorems here, and this is your current state of math. Now, you have a different bucket of theorems here, and then you end up with the same collection of theorems at some point in the future.
But the point is, so if let's say you have at some fine level, right? You have 2 students, 1 exam, 2 books. They both pass the exam using different books. Okay, then those books offer some equivalent result, right? And then, but you could kind of scale that to some sort of field of study. Yeah,
you're right. But you're right.
But at some point, not to get into necessarily the whole homotopy business at this point, but at some point when there simply are open questions about relations between different higher levels of math, you can think of these as these kind of higher paths where you have some community, they're able to engage in these different particular pursuits, but they're more or less working in the same field, but there are certain bridges that we're still trying
right
to
well that's called
build.
That's critical pairs, because look, the point here is what's happening is, and by the way, this is very pro Plato, because what this is saying is you may take different paths in mathematics, but causal invariance means you'll always be able to wind up in the same place. Right? That is, that whatever, well, I think the ultimate thing is more, ultimately it's more like the Rouliad story, that in the end, even though, what all you're doing, in the end, all of possible mathematics is in the Rouliad, and the particular historical mathematics that we've chosen is a particular slice of the Rouliad, and we get to see a simple version of that here, that you could have proved different theorems, but in the end, you have the same, you can get to the same place. Now, this question about, okay, so now the question is, what about the whole community of mathematicians, which have a different, where the question is, how big are they in branchial space? How big is a field of mathematics in this branchial space? So in other words, each individual single-minded mathematician is going down a single path. But it could be the case that the mathematician knows full well that there is an equivalent path here.
Right. That's what you get with a community. Alice knows, let's just call them Alice and Bob some mathematicians, right? Alice fully well knows that Bob did his PhD thesis and went on one particular path, but she knows that she can also get there via some other route. This is what you get with a community. You kind of have some understanding of other paths that have been taken.
Right. Well, okay. So in a sense, we can map of math community. Okay. So mathematical communities, this is a very bizarre thing, are basically laid out in branchial space.
Right. That's a good tagline for funding, I think.
I don't know. Okay. In any case, so one mathematical community in this model where there's a single-minded observer following a single path, right? A mathematical community is a blob in branch Hill space,
Okay.
and with certain common ancestry. They're not far apart in branch Hill space.
Right.
A given community has enough common ancestry to be close in branch Hill space. Okay, so here's where it gets really crazy. Look at the math genealogy database and see whether we can map out, is the math genealogy database a map of branch Hill space?
It could be done.
Well, right, we have all that data.
Oh, that sounds like a good project.
Well, I mean, okay, so what would that look like? I mean, that would be, so what we would see there is we would see what we'll see is the student, this is a graph of, studenting, so to speak. I know there's hold on one second, I'm going to just pull this up. I think we've had some totally weird interaction with the math genealogy project where they were like, we want the data to be available to everybody. And then we said, okay, well, we'll put the data somewhere. And they're like, oh, no, but you can't put the data there. It's like, okay, great. But I don't know what's happened with this. All right, so this is an exploration of, I want to see the graph. I want to see it in branch Hill space. We should be able to see this. That's amusing. Come on, are we going to see, bro? What is this? What is this? What is this? Transitions accumulated between different fields. Oh, look at this. We might be getting somewhere here. Well, that's, I mean, okay, so we can clearly get this data and play with it. That would be very amusing if you could actually see, let's think about this. Yeah, I mean, the claim would be, it's pretty similar to this graph because you got to the same place and then, you essentially have a student here. And that corresponds to a different, that then produces a different set of outcomes, but there is a shared common history. And then this convergence process is the thing you're talking about correspondences between fields somehow.
Yeah. Like the classic being like the Langlands correspondence or something.
Right.
Yeah.
All right. So this is a weird, crazy piece. Okay, so people are asking on the live stream about the relationship between inference rules and axioms. Okay, so we've been quite confused about this. We think we've understood this now. Let me explain what we think we've understood, okay? We think there are two different ways you can model mathematics. One, which is the one that I adopted in NKS, involves the nodes of the graph are expressions, and the theorems are basically correspondences between expressions. Actually, that was only one way. I did it in two ways in NKS. Okay, sorry. No, actually, let me retract that. There are two ways to think about this. One is you have a certain set of axioms, and the edges of the graph are, well, let's look at a token event graph. The edges of the graph are somehow associated with the application of axioms. So in other words, you get from one proposition to another by ultimately applying axioms to it. Okay, that's model number one. Model number two, which we think is closer to what's actually going on, is mathematics consists of a giant vat of propositions, theorems, a giant vat of true theorems. Okay. And the way that mathematics progresses is by taking, for example, pairs of true theorems, applying a law of inference, and deriving another true theorem. So in other words, it's much more like what we're seeing here, where this is our vat of true theorems. There is a law of inference here, which in this case can derive 3 different theorems, and those are the results. And then now our vat contains, well, we didn't deduplicate these nodes. Here, I think we did do the deduplication. So this is showing how this vat generates extra theorems. So that's the model. So now the question is, as we generate, right, so all that's happening is that, our law of inference, given 2 theorems, it may or may not be able to combine those 2 theorems to make another theorem. And for example, a substitution lemma can do the combination when one of those theorems is an equivalence theorem, so to speak. Whereas probably other rules of inference can be applied when, in other words, what law of inference, law of inference will typically be applied to two theorems, and which kinds of theorems it can be applied to, different laws of inference will have different diets, whatever, different one of them is a herbivore and it eats equivalences, and another one is something else.
Lithophage, rocky.
Yes, for example, the lithophage just passes through the theorems unchanged. As we learnt, crocodiles apparently do with rocks.
Might be alligators. Anyway.
Oh, is it alligators?
I just don't,
okay,
never mind. Get it wrong. Yeah. Well, should Stephen, do you want to test out some examples of some different inference rules, or is that
no?
Not
I
the
want
dire-
to.
Not the
No,
direction?
I want to go. The real thing I want to do is to go to troughs.
Okay.
Okay. But I think what I'm trying to understand here is, in this model, we've got here, what does the continuum limit of all of this look like? In other words, the continuum limit is something where we have equivalents together many, just not think about this, in the space-time case, the continuum limit is very coarse relative to individual atoms of space. It is equivalence many, many atoms of space. Or perhaps said differently, it's equivalence many hyperedges. And so what I think is happening in math, okay, so in a sense, many hyperedges are equivalenced. So what does that mean? Valenced. In space, that just means we're looking at things at a coarse scale. In mathematics, it means somehow, this is the essence of what a mathematical observer is doing, the fact that there are many different statements of the Pythagorean theorem with many different, it doesn't matter. All you care about is the Pythagorean theorem. You don't care about the fact that you can state it in, okay.
Well, except for the fact that the different approaches that you take, okay, it doesn't matter in terms of the Pythagorean theorem, but then when you continue thereafter, the consequences of those individually might make, they might have different results. So I think the direction that you take, it could still be important.
It's possible, but I think the question is, okay, so what's a good example where we've got a theorem that can be stated in many ways, but we still say it's the same theorem? See what I'm saying? So
Yes,
just a very elementary theorem in arithmetic, for example, that they've got to be, I mean, we certainly know we can have different proofs of a theorem, but this is going beyond that. Not just different proofs, but a different statement of the theorem.
Is it more about axioms, but not theorems? Like you have different axioms, what the real numbers are.
Oh, I see what you're saying.
Then theorems that use real numbers obviously are also stated differently, in a sense.
Well, that's a good point. That's a good point. So, e.g., with different axioms for the reals, you can still get a quotes Pythagorean theorem. Right, but the question is when is, I mean, because this is the essence of what it means to be a mathematical observer, that you care about. That's why the working mathematician doesn't care that much about the axiomatic foundations, because at their level of sort of fluid dynamics, those two statements of the Pythagorean theorem, even though one is using Dedekind cuts and one is using Cauchy sequences or whatever, it doesn't matter. Because they have a version. What's that?
Yeah, this is an important point.
Right.
Yeah,
But,
I mean, what just for the, we've discussed this before, but just I suppose for the audience, I mean, this is, we're thinking about this in part due to the popularity of automated theorem proving and trying to understand the relationship between relatively, how can we put it, kind of carefree mathematics that most working mathematicians pursue, and this kind of what we kind of think of as molecular mathematics, where you're looking at the foundations, you're looking at the axioms, and to what degree it matters for the working mathematician, because many people who are just practicing mathematics don't particularly care about that fine degree of resolution. And the question is, are they right not to care, or do they need to care?
Well, I think it's the same reason as, can we do classical mechanics and not do quantum mechanics?
Right.
And the answer is, most of the time you can do classical mechanics. If you design a car with quantum mechanics, it's probably a waste of time.
Yes, but there is a kind of there is, molecular revenge, so to speak. If you completely ignore it, you'll be
right. There are cases in which there are problems, which is basically, various kinds of undecidability in mathematics are such problems, probably.
Mm-hmm.
But I mean, here's a bizarre analogy. The analogy is, in thermodynamics and statistical mechanics, actually, this is an amusing and absolutely bizarre analogy. Why is undecidability uncommon in mathematics? Okay, so this is a claim.
Mm-hmm.
And the claim would be, for the same reason, question mark, for the same reason that gas molecules in a gas usually have a short mean free path. Okay, so in other words, if you've got, if you're thinking about, it's like, well, there could in principle be a single molecule that makes it all the way across the room. Okay, but most of the time that won't happen. Most of the time it will be thermalized into just a random, properties of a gas. And similarly, in the case of undecidability, occasionally there will be something where, that proposition, so to speak, escapes out to infinity. But most of the time, for most mathematics of the type, it's as if, okay, so the claim would be, claim in this thing would be computation, e.g. rulology, or NKS type stuff. Oh, yeah. That's still a spelling word. Okay, computation is like free streaming molecules, whereas kind of human processed math is like is like a gas where the molecules are all where it's making any sense. In other words, the act of sort of human processing of math is the thing that is forcing you to have all of these, the equivalent of these different interactions. Whereas when you just say, I'm going to write down a computation and do something, it is not dealing with that. This isn't quite right, but there's something.
I like to think of density of proof space as another analogy for thinking about this.
Well, that's a different issue, I think. I mean, okay. So the question is, let's see, the question is, okay, the question again is, when are two Pythagorean theorems the same? So Nick has made the good point that two Pythagorean theorems from different axiomatic systems, which, by the way, we should find an actual example of that from Lean and Metamath and so on. We should get explicit examples of that, of what the different Pythagorean theorems look like. But why do we call them the same Pythagorean theorem? What attribute do they have that makes them the same? I mean, they're really only the same in the eye of the human observer, I think. In other words, given two different axiom systems, how will we determine that this is, quotes, the same theorem? Right, so that's the question.
You have to coarse grain. The
right.
Mathematical definitions.
Okay, so given two different axiom systems, can we determine whether two differently stated theorems are the same? And they're clearly not ultimately the same. They're clearly ultimately different.
Yeah.
Okay, let's take an example with groups, where an individual group is like a different axiom system. Okay.
Each group, a different axiom system.
Yeah, each group is like a different axiom. In group theory, each group is like a different axiom system because it's added the actual relations of the group.
Okay.
Okay, so now let's ask this question. When are two differently stated theorems are the same? So what that would be, actually, even each group is like a different axiom system. Actually, even each presentation of the group, each choice of generators. Okay, this is interesting. So basically, we've got a group with two different presentations. And we're asking the question, so we got some random relation in terms of words, stated in terms of one set of generators. We've got another random relation in terms of words, stated in terms of another set of generators. Yeah. Is it the same theorem? So how would you tell that? What's the criterion? Because you could have even, you could, if I'm not mistaken, maybe I'm confusing my group theory, but I think you can even have a different number of generators, can't you? Do you have to have the same? Yeah, you can have a different number. So when are two theorems? I mean, it's like maybe this is the essence of representation theory, actually. And I think then, yeah, okay. So I don't know whether anybody knows this math here. I think there are these things like, I bet this is a case. I mean, I don't know whether either of you know this math well. I do not.
Not terribly well, though I do wonder how irreducible representations fit in. This was discussed, I remember, like a few months ago during a live stream, I think with Tali, but I think in a different context.
Yeah, I think this is just pure, hard-nosed group theory, so to speak. And I think that I have this vague recollection of this kind of way of let's see, of taking relations and kind of seeing how they transform from one representation to another.
Well, here's the thing. So if we take homotopy type theory just as an example, part of it is we still have this idealization of a type. So the type can have different inhabitants. They're distinct, but we have this idea of intentional equality. And so you can have these different constructors of the same type be equal, or there's some sort of path or something between them because they both generate the same type. But the problem is you still have this idealization of that type. And if you think informally about the Pythagorean theorem, it very much helps that we have idealizations of triangles and edges and lengths, etc., so that you can take these two different proofs, but you still have some common idealization in order to think about them. And it's not clear to me how that manifests in our models, and whether or not it's helpful to think about it that way, or if we need something more fundamental. Like, basically, how do we get these mathematical concepts that helps us to make sense of these different proofs that we produce?
I understand. So the issue is, this relates, in the case of space, we have the kind of metric properties of space. We could be very, very confused because we could be looking right down at the level of atoms of space, and it's a big complicated mess. But we think we can characterize space in terms of things like curvature.
Mm-hmm.
And that becomes our kind of human level description of space. Space is described by curvature, aka gravity, and so on. Now, and let's see, the properties of space, in a sense, okay, so let's play the following claim. Okay, so relative to physical space, okay, in physical space, consider Euclid. Okay, consider that so what we're saying is, okay, so this is an example. Different underlying hypergraphs, all limit to satisfying approximately, and the word approximately might be important, Euclid's axioms, and all the propositions of Euclid's, plus Euclid's theorems and so on. So it's not at all, so each one will do it in a different way. See what I'm saying? So if we say, let's take apart the triangle inequality, okay, what does that mean for a space built on this kind of hypergraph? Well, you could say we can decompose the triangle inequality into this weird collection of relations about, the multiple applications of this rule. See what I'm saying? But another hypergraph would have a different, essentially, representation of the triangle inequality. Probably this is something you can do just on graphs without limits. I'm not sure, but the basic claim would be that this is an example of exactly the same phenomenon. That is that you can end up with, in the space of different hypergraphs and hypergraph rewriting rules, many of the same theorems will always be true. That's the claim, that there is a continuum limit,
right?
And that the continuum limit is independent of those details.
Mm-hmm.
And so that's also the claim that mathematics is inexorable, independent of its axiom system. That certain aspects of mathematics ultimately don't depend on the micro details of the axioms. So the question is, some aspects of mathematics, like, for example, we believe that the dimensionality of space depends on the underlying rule, at least the presumptive underlying rule, will affect the dimensionality of space, but it will not affect, within a large class of rules, it won't affect the fact that space exists at all. So similarly, in mathematics, we would expect that for a large class of rules that, we could have Euclidean geometry, we could have non-Euclidean geometry, different rules will lead to different things there. But the claim would be that some essence of the mathematics is independent of the rules. That as you move the underlying rules around, the observed mathematics won't change very much.
I mean, there could be some rules that I can imagine rules that just aren't expressive enough, though.
Sure.
To yield anything.
Right. I know, but it's the same thing with, look, there are rules where the universe will be dead in 10 to the minus 100 seconds.
Yes.
Okay. And it's all over. And, this question and how that, we've got another level of how that works with the Roolead and real space and so on. But ignoring that, if we say we're throwing a particular set of rules, and then we say, what consequences do these rules have for physics, for mathematics?
Mm-hmm.
The claim is that there's a continuum limit of mathematics for which the details of the rules don't matter very much.
Right.
And okay, so
I see. So it would only be a problem if you happen to have access to some corner of the Roolead with only, highly unexpressive rules. But perhaps you wouldn't necessarily. But if that was the case, maybe there. This gets back to questions like the anthropic principle. Do you think there even are observers?
Let's come to that in a second, because I've got a different idea about that. But let's make it one point about group theory. Okay, so the question is, what results are there in group theory that are essentially that are sort of continuum limit results, independent of which group you're talking about? And clearly those are, you see, what we really want are ones which are, there are results in pure group theory, which are of this type. Okay, the thing that will be interesting, but what about results which are approximately true, which are roughly, which are roughly true for any big group, or any big representation? You see what I'm saying? In other words, because that's the analogy that we want. We want, kinds of results which are independent of the axiom system, but, maybe there's a little bit of glitching around the edges, but in some limit, they're independent of the axiom system. But coming back to your point about mathematical observers. Okay, so what is the difference between a mathematical observer and a physical observer? Basically, a physical observer lives in the thing they're observing and has no choice about doing so. A mathematical observer, we believe mathematicians do not live inside mathematics, except insofar as they live in the physical universe, which has certain, which is also in the Roolead, but it isn't. You see what I'm saying? And in the case of the physical observer, when we say, for example, in quantum mechanics, we have branching brains which are perceiving the branching processes in quantum mechanics, we're right down there in the quantum mechanics, so to speak. The mathematician is, this is one mathematician, there's another mathematician. They are not intrinsically, they don't have the same intrinsic living in the mathematics that we have with respect to living in the physics. Did that make sense?
Well, I know Nick has made some interesting comments about this, about the degree to which physical rules that inform the universe that you inhabit, this in some way should probably also inform the kind of mathematics that you observe.
Physical rules and mathematical rules are basically in the same pocket of the Roolead.
Well, that would be a claim. Okay, so now your claim is going to be made. The only math that we think of doing, possible claim, the only math that we think of doing is math informed by our experience in the actual universe somehow.
Yeah,
So
it's
in other
hard,
words,
right? It's hard to describe it in anything but really kind of rudimentary terms. But like counting surfaces. I mean, you can kind of see how numbers in geometry, for instance,
I know. I wrote that whole essay
familiar.
about whether numbers are inevitable.
Right, there you go. Yeah, right.
And my claim in that essay is numbers are inevitable. Okay, so the claim is, e.g., claim, numbers are inevitable given sort of basic physical consciousness. In other words, they are related to the single thread of experience, persistent, coherent observer type stuff. Actually, probably that's basic geometry is probably a consequence of that too.
Well, that's what I was suggesting. Yeah.
Of our sort of consciousness / our, our character as observers. So the basic claim is there is a lot of math. This is very interesting in sense of the math inventor discovered whole question, right? There is a lot of math. I mean, the basic claim would be there is a lot of math that exists in the Roolead, but that we never sample. And you see one thing about physics is that there's pieces of physics that we turn into things we can understand. There's lots of physics down at the level of atoms of space that's doing all sorts of computationally irreducible things that we will never, that we don't really have any chance to understand. And we can understand them microscopically, but when we look at the large scale version of what they do, they're doing irreducible computation far beyond what we could possibly do, given that we're embedded in the same situation, et cetera, et cetera, et cetera. Mm-hmm. But, the fact that we end up with comprehensible physics. Okay, so the fact that we, claim we end up with comprehensible physics for the same reason we end up with comprehensible mathematics.
Well, sure. I mean, that's in part why we're doing this MetaMath project, as we're also undertaking the physics project and using similar multi-computational models, right?
Right.
Yeah.
Okay, so basically the point is, it could be the case. Mathematics could be full of computational irreducibility, just as physics is full of computational irreducibility. But there is a slice of physics that has reducibility and has laws that we can easily state. That slice is the slice that is taken by a consciousness like ours, by observers like us. So the claim would be the same is true in mathematics. That there is a mathematics, which is the mathematics of the sort of rheological mathematics, the mathematics of arbitrary computations, that is full of undecidability, it's full of really complicated things, but the slice that we humans take is a slice that has reducibility. And the claim would be, and this is a different, the claim would be that the character of mathematics that we do is informed by our by the sort of physics-like properties of our consciousness. And probably central to that is things like geometry, or perhaps the notion of a continuum. I mean, maybe the notion of the continuum is, okay, so the next question would be, is the notion of the continuum deeply related to our to sort of the character of us as observers. Which kind of gives a lie to, well, the Dedekind statement, what was it? Integers are the work of God, and the reals are somehow of human construction, so to speak. That kind of, the question is, do all observers like us? Does it come with the notion of an observer like us that we will conclude that there is a continuum?
So
what
do you mean like us then?
Well, I mean, by like us, I mean computationally bounded and with this notion of persistence. Oh, that's probably the key. Okay, so look, the thing that makes an observer like us is that our nature is somewhat persistent. That is, at two successive moments in time, we at least imagine it's the same us that's making the observation. It's not the case that at this moment it's one observer and then the next moment it's a completely different observer. There's a notion of actually, one would even use continuity between moments in time, right?
Or persistence.
Continuity / persistence between moments in time. For the observer, right? So the observer has continuity or persistence between moments in time. By the way, the observer also has continuity and persistence as they move around in space. That's this idea of pure motion. The fact that pure motion is possible, as I move, I am occupying different atoms of space make me when I've moved to a different place. But yet there is a notion in which I stay the same me, even though I am made of different atoms of space. And that's the same idea. It's just like, it's the same me at different moments in time. I guess the way to put it is, it's the same me at different moments in time or different places in space. So now the question is, does that lead us inexorably to the idea of a continuum? Because if it does, then I bet it does. And I bet it does for the following reason. Yes, it has to, for kind of Zeno-like reasons. Here's how. Okay?
Yeah.
So imagine that it's you now, okay? A minute from now, it's not you. Okay, what about, I'm not making this argument perfectly, but you see what I'm saying? If it's going to be you a minute from now, it's also got to be you infinitesimally from now forward, so to speak. In other words, if you're going to be, if you're consistent for a whole minute, you're consistent at every point in the course of that minute. See what I'm saying? It has to be the case. In other words, that to get to the destination, you have to go through all the intermediate steps.
Yes.
And any intermediate step you can describe, even infinitesimally in the future, must be included.
It's a little complicated because on the one hand, you have to have some rule that preserves, I would say, physically me or any observer as an observer. Okay, that persistence has to be maintained. But then there's also this question of the mathematical evolution and the way in which the observer, this is the trouble. How are we going to think about in parallel the physical observer and the mathematical observer? How, to what extent?
Well, okay, so here's my claim. My claim is that, which I hadn't realized before, that the observers like us constraints inexorably lead us to the idea of the continuum. Because of this point, that if you're going to be the same you throughout time, right? you have to be the same U at every infinitesimal moment of time. It's kind of like I think it's a physicalization of the construction of the reals.
Yeah, but the question is, when you say continuum, you're talking about in metamathematics.
No, I was thinking about the continuum. I was thinking about the notion of a continuum, right? Which at first is a continuum in time. The claim would be, okay. The right. Claim is persistence of the observer implies, I had not realized this before, but this is kind of an obvious point, implies a perception of a continuum. Because otherwise, there's, the observer.
Sure. Because there's discontinuity.
Yes, right. Yeah. Otherwise, there would be a discontinuity. That the whole notion of persistence of the observer is a notion of, and in fact, the same is true. Okay, this is a good way.
Yes, I understand. I mean, you can imagine a Zeno-like situation where you have someone recording their observation at arbitrary time scales, right? But if at some point that little homunculus doesn't show up and doesn't make that particular recording at some arbitrary period of time, then you have some discontinuity. And it's because that little homunculus didn't show up and make that recording. But in this case, with persistence, it's actually it's some consistent notion of the same observer every single time.
In other words, there is the assumption that there is no coming and going homunculus.
Right.
There's the assumption.
Yeah.
Well, but the thing is, the truth of the situation is, if I try to move 10 to the minus 100 meters, okay, there might not be any place for me to move to. But I nevertheless have the perception that there's always a place for me to move. If I'm just moving quotes in a straight line in space, even though in reality, that's happening by a series of, microscopic, processes that are not, in fact, if I were to look at, a piece of me and I were to say, there is the surface of me, it's precisely at this point. In fact, like in computer graphics, so to speak, that surface as it moves is, it's pixelated.
Sure.
But it is my conceit, in a sense, that, I have this, that it's just me moving around. It's always the same me, independent of the fact that, in fact, I get pixelated differently as I moved in different places. So that's the physical experience.
But the trouble is, if we're going to speak about continuity in metamathematical terms, you see, so far we've been treating that as some property of the actual entailments themselves, whatever rule informs the entailments, not some rule that informs the observer. So how to actually think about the interface of the two of these, I think it's going to be
here's what I'm thinking. The basic question is, what is the coarse graining procedure? Well, coarse graining is kind of the dirty underbelly of statistical mechanics and many other things. It's like, because it is ultimately a model of the observer, which nobody wants to have. In quantum mechanics and statistical mechanics, in general relativity, and in cosmic censorship hypothesis or whatever else, nobody wants to have that model. Nobody wants to make that model. It's a messy model, which is why we have to invent this observer theory to try and clean that up. But that's a different issue. But well, that may be related.
It's related,
right? But so the question here is, what is a plausible mathematical observer? And of all the possible, down at the level, okay, you've got this thing, it's written down in symbols, it's at the axiomatic level, and the question is, what do you notice about it? And my claim is that, in the origins of mathematics, what were the origins of mathematics? Basically, arithmetic and geometry in Babylon. And both of those So, we could imagine, as we do in NKS or Ruleology or whatever else, that there is de novo invented mathematical-like stuff where you just throw down an axiom system and say, what does it do?
Yeah.
Okay?
Right.
That is not what human mathematics is concerned with. Human mathematics instead concerns itself with things which are essentially humanizable statements, like the Pythagorean theorem. And so the question of what, right? So the claim would be you have different underlying axiom systems, but they still emerge to give you the same continuum of the Pythagorean theorem. And the issue here is how do we understand? Just like in statistical mechanics, we can readily understand that different molecular interaction laws give us the same fluid dynamics on a large scale. And we can sort of prove that. The proof is a bit rickety, but we can sort of prove that. In what sense? Okay, what is the limit that we want to get? In other words, is there an inexorability to some aspect of mathematics? Just like we think there's an inexorability to certain aspects of statistical mechanics and certain aspects of fundamental physics. The inexorability in fundamental physics is Einstein's equations and the path integral. The inexorability of statistical mechanics is essentially gas laws and fluid dynamics, or actually more the second law of thermodynamics. But now, so the question is, what is the inexorable limit that, the question, what is the inexorable limit for an observer like us of this metamathematical process? I bet that this persistence of the observer thing, I bet that has a consequence for thinking about these things. I bet that means
you can think about them at all, for starters. But yes, beyond that.
Well, but the issue is, the observer is interested in those things which persist.
Well, yes, but there are ephemera. But they
but not down at the level of
right. But those have to have some duration as well.
Okay, so the claim would be the observer typically cares about phenomena that persist. So something which is a detail of some automated proof that has no persistence is not going to be noticed, so to speak. So what is it about, if you look at the proof of that Boolean algebra axiom of mine, one of the problems is it's all sand. It's all very detailed stuff. There is no bigger picture, or there doesn't seem to be a bigger picture. How would one identify, from an automated proof? This is the thing we wondered about for ages. From an automated proof, can we recognize a bigger picture?
So what do you mean by a bigger picture in this sense?
Well, okay, let me give you an example. Okay, so where is it? Let me look here. I have to find something. Okay, so here I was talking about exactly this issue, right? So we got this proof, and it's got all these pieces, and it's got all these intermediate propositions, and there's some that are more used than others, blah blah blah. By the way, that should show up. I don't know what the significance of that is in our token event graphs, because this is a slice of a token event graph, basically. Okay, so the claim made somewhere here. Okay, this is my claim about the nature of explainability. Okay, so the basic point is, imagine this random cellular automaton. Okay, it's got all kinds of detailed stuff going on. And then it's got this glider. And we sort of know to call that a glider.
Yeah.
it's a persistent thing, as opposed to the fluff up here, which we don't have anything to say about.
Right. Well,
other than that, right. Right. I noticed Richard, there are lots of interesting comments on the live stream, which I want to look at here. Richard is commenting on persistent homology of observers. Yes. Yes, I wonder.
That too, right.
I wonder. I was thinking about that. I mean, what's the analogy? Persistent homology would be a story of some sort of topological stability. That's short-term topological stability somehow. Anyway, let's look at some of these, and then I want to come back to troughs, which was my original goal.
So anyway, you were saying about this glider. Yes,
I was saying about
the glider persists. Yeah. These other ones are, I mean, they terminate. These ones terminate. Yes,
I know, but it could generate random fluff forever. That's not the point. The point is that the glider is a persistent structure that we can talk about.
Right.
So in other words, we could have a structure like that. In something like this, okay? We could have a glider. We can also have a bunch of persistent crud about which we have very little to say.
Mm-hmm.
Right. So there are persistent features, and there are things that are just down at the computational irreducibility level.
Right. But the same rule.
Yeah, right. Okay, a comment from Richard here, and then I want to go back and look at some other comments on this live stream. Bigger picture, are we stuck? Can we jump to other disconnected components in mathematical space? Can we generalize, like finding the least general unifier, persistent topological features, localized patch of Poincare recurrence, not necessarily in the structure, but some property at least. So that's a good question of whether, I mean, this is a thing that I tried to address in that Rouliad piece I just wrote, is, what is the world like for the aliens? The answer is we're pretty stuck, is my view. We're pretty stuck if we want to have, if we're going to be like us, we're pretty stuck. In other words, you want to take a trip to the next galaxy? No problem. Just become a photon. The problem is a photon isn't like us.
But are we stuck? If he means, are we stuck in metamathematical space? I mean, I still think that our reach, our grasp, our extent in metamathematical space, I mean, it's growing. It is growing.
Yeah, it is.
With abstraction and with our ability to identify connections between different
right, it's hardly surprising it's growing. Yes. There's a geodesic ball that's getting bigger in this.
So I wouldn't view it as, there's some mathematical space and we're in it. It's our practice of mathematics that is determining our reach. And I think it's growing.
Yeah, right. But so the question is, are there topological obstructions? Is there an event horizon in metamathematical space? That, in other words, can we just continuously diffuse outward in mathematical space, gradually, getting a little bit further? And this relates again to homotopy type theory and the question of whether there is non-trivial homotopy in homotopy type theory, so to speak.
Well, there can be. Yeah, I've suspected that, the presence of some sort of genus or obstruction, but it depends on in what context you're referring to it. I think that it can, so if you have some hole, it means that if you're going to get to the other side of that hole, you have to go around it. So there's some circuitous path, some long path you have to take. And so I've for quite some time suspected that there's some way of discussing computational irreducibility and maybe even computational equivalence in terms of
I see. Your claim is that it's a very okay. So the question is,
so if you find some Swiss cheese like space,
right,
it might just be really difficult to navigate it, and it might require computational tools that extend beyond. Like we might need quite a bit of assistance to.
Okay, so
find
the question is
side.
metamathematical space like Swiss cheese, so to speak? In other words, with many obstructions, with many topological obstructions.
Mm-hmm.
And the question is, and in fact, does computational irreducibility imply that this has to be the case? I don't know.
Yeah, I mean, part of the problem is this is something that's been discussed before, at least with homotopy type theory. You don't necessarily think about the length of these paths. It's just exciting, at least in the beginning, to think about paths and think about their equivalences. But as soon as you think about the length of the path corresponding to, say the number of operations involved in some computation, if you have like some kind of metric, for instance, then you can probably start to tease out these questions more. And the question of whether or not that's what's of interest to the people who are advancing homotopy type theory kind of remains an open question. But I think that this idea of looking at lengths and trying to think about computability, not just like whether or not it's computable or not, but in with computational time complexity, whether or not we can actually expect to be able to compute these even with computational assistance. I think that that's all exciting work that hasn't really been done yet.
The question is, in rule space for Turing machines, this should be an answerable question. That if we look at, I'm trying to think, if we're trying to go, I think there's a question of what is the topology of that space? And I've drawn those spaces. So I think they don't have a lot of, the ones I've drawn, boy, actually, this is interesting. I don't think I've really looked at them topologically. I mean, I think even in the Ruliad post, I had a picture of one of them. Let me see if I can pull it up. I don't know whether purple is the best. Anyway, never mind. We can theme in color for. Okay, so this is an example of a piece of real space for Turing machines, and it does appear to have big holes in it. I don't know how one classifies that or whatever else. There we go. There it is. I don't know. That's a good question. What is the topology of that space? I mean, I know for finite Turing machines, it's very compact.
Right.
But I don't know what it is for. That's a good question. All right. Anyway, let's look at some other comments on the live stream.
Okay. And also, Troughs.
Troughs. We really want to look at Troughs. At least we want to get started with Troughs.
Imagine Nick will have something to say about.
Nick is going to have lots to say about Troughs.
Yeah.
Okay. So AK comments, what if the glider is not persistent and the fluff is persistent in the bigger picture? Yes, absolutely. We don't live forever. As persistent observers, as we are, on the timescale of the universe, we're not very persistent. And so, yes, again, the theory of the observer is mushy because things like, well, we're persistent, but we're not that persistent, yeah, Mark is commenting this question about continuum is related to the question, do you actually need calculus? I think, yes. I mean, I think that it's rather fascinating, actually. Calculus is a way of humanizing which is actually a very bizarre thing to say because, right, people are always complaining about how non-human calculus is. But in some sense,
is that the epithet that it's non-human?
Oh, I don't know. I mean, I mean, it's best done by computers, not by humans, type thing. But that's an irrelevant sideshow. But the basic point is that yes, I think that would be the claim. The claim would be that calculus is a language. Basically, calculus is what the claim there would be calculus is the linguistic construct that connects observers like us with physical reality.
Mm-hmm. What do you mean by a linguistic construct?
Well, I mean that the idea, we could be describing things down at the level of atoms of space, but that is not something that observers like us can really deal with because it requires computational unboundedness and so on. If we're going to describe it at a level that observers like us can engage with, then the claim would be that we need the continuum somehow. So in other words, that the continuum is the description language that observers like us use to sort of have to use for reasons which I had not realized before. This Zeno-like argument about why the continuum is inevitable for observers like us is interesting. Let's see. Okay, so another comment here from Mark. The execution of the rule gets you from one discrete state to the other. The rule is the continuum, but you don't need continuous time. You just need to glue the correct discrete time samples. Yeah, that's absolutely correct. But the concept for an observer like us that we persist through time, we're not saying we only persist. Our perception is we actually persist through time. We persist from this time to that moment an infinitesimal time later, to the next one, to the next one, to the next one. We don't have the perception that we go in jumps. That's the claim. The claim is that our simplified version of time is a continuum notion of time.
We're just glue ignoring machines, right? Constantly.
Right. And so our perception is that time is a continuum. There are no discrete, not us, so to speak, steps. Because if there's a discrete step, there's a moment at which we're not the same. Okay, let's go back here.
Troughs?
I just want to look at these comments and then we're going to get to Troughs. Richard, the CW complex is an interesting structure from homotopy theory, but the limiting object should generalize all possible underlying structures. I can't comment on that.
Where is that comment? This is from Richard.
High up on there. Richard's commenting on in unification, they're interdependent substitutions. That was what Nick was talking about earlier. Textbook defines your place in real space since it defines the substitution rules you can apply. Potentially, although you can have different textbooks, it might be at the level of the rules of inference, or it might be simply at the level of these are the theorems we're proving. Okay, LB, adding theorems by applying an inference rule is going down one branch in the graph, and adding axioms is the completion equivalencing procedure. Is that interpretation correct? Not quite. I think we kind of went through that there are these different ways of interpreting, of modeling metamathematics. The one that seems to us most promising is this kind of vat of propositions idea, where all the known true theorems of mathematics are all floating around in this vat, and mathematics progresses by picking up, by two theorems coming together, having an event, and producing another theorem. And that gradually there are more theorems that assemble in this vat. And that, actually, here's another point. The initial conditions, you could say, well, why don't you just put all the theorems in there at the initial condition? The problem is that would include theorems which are, I don't quite see how the inconsistency thing works. In other words, because if we were indiscriminate in choosing initial conditions, we would have both theorems that we consider to be true theorems and theorems. In other words, we could perfectly well say both P and not P and have those be initial conditions. And if we do that, we'll be able to derive everything.
Mhm.
I mean, again, this is some complicated thing about slicing the Roolead, which let's not get into right now. Liam, could one describe this as mathematical frames, paths in broad shell space, co-evolving with the environment?
What's the environment in this case?
Well, I think this is the question of whether, okay, there's another messy question, okay, which I tried to talk about a little bit in that Roolead post, although not as much as I might have done, which is to say, as technology advances, do we change our reference frame? In other words, a human who has, augmented sensory information will eventually not only end up, will end up with essentially a different cognitive framework. And even that's what happens in sort of the paradigm shifts in science thing. It's the same type of story. And how that works relative to, again, the co-evolution, that's an interesting and messy issue. The co-evolution of the observer with the universe, so to speak, or with the mathematical universe.
I mean, one problem is if, just to frame this with respect to this idea of the molecular and continuum dynamics, say, of mathematics, it could be the case that, yes, you have more advanced, especially information technology, you basically have, or you can do finer computations, and they can be used as tools that can be helpful, but they kind of do kind of computations that you yourself might not do. And so it's kind of helpful as an instrument, and it can help you perform new observations. But I would say that expanding our reference frame itself, I mean, I still think about that in terms of knowledge, abstractions, more comprehensive models.
Yes.
And we can have tools that can probe into finer levels of detail, but the important lesson is not to get lost there. Set something up so that you can extract what you need from that kind of probing, but to continue to expand abstraction and knowledge, which I think that's okay.
But let's give an example.
Yeah,
okay,
yeah.
We have, if we look at the history of technology, we have a bunch of different kinds of sensory information that we get: microscopes, telescopes, amplifiers, all kinds of things. Right? Every time we bring one of these in, it ends up, for what seem like anecdotal reasons, but probably they're not, bringing us a different cognitive framework for thinking about the world.
Yeah.
And, the biggest one in recent times is computers and computer experiments.
Mm-hmm.
And that's given us, I mean, story of my life, so to speak, given us a different kind of cognitive framework for thinking about the world. And so you might say it's mere technology. And this is why observer theory is a mess, because basically you say it's mere technology. Okay, you can do these computer experiments, but that leads to something that is very mushy and very non-theoretically describable, which is our current understanding of sort of computational things. That's not something where we can sort of, okay, in mathematics, the goal, partly with Euclid, but partly 100 years ago or so, was let's axiomatize it. Okay, I don't know of the way to axiomatize general understanding of things. And I don't think, as I suspect that the axiomatization of mathematics is slightly a red herring. But in other words, to say, let's take what we knew before Galileo, what we knew after, let's take what we knew before sort of the idea of relativity or something and after, and let's ask the question, can we kind of, can we axiomatize our cognitive framework? And I think that's difficult. I mean, perhaps not impossible, but difficult, and may not even make sense. But that's what we need to be able to say, given that we have the idea. Okay, it's my famous example is fractals. Okay, the idea of fractals, the idea of making a Sierpinski pattern, is not a difficult idea. You know, you show it to a young kid, they start doing it, pretty soon they've drawn tons of them. It's not. However, in 1210 AD, somebody had this idea. They made mosaics out of it. Art historians commented on those mosaics for centuries, never mentioning those patterns. They were just completely blind to those patterns until along come fractals and things, and then they talk about that. Well, I think actually I might have pointed out that it's there, but they now talk about it at least. But now they're not blind to it. People are not blind to it. But for a long time, they were just completely blind to that because the cognitive framework that people had didn't talk about nested patterns. And so similarly, you know, I think that the things that will be the most, you know, we feel a bit embarrassed about the progress of science in the future will be things where, and I think there's going to be a big one in molecular biology, but that's a different issue, where it's like, you know, we just didn't think that mattered. We didn't think that was a thing worth looking at. I mean, I'm sure the same is true with, you know, germs, right? The theory of people didn't know. People had the idea, oh, you know, they had all kinds of crazy ideas. And then it turns out there's a subtle thing that people hadn't really looked at that ends up being the explanation for what's going on. And I think each of those things is, you know, that's a piece of the progress of science that I think it's hard to capture in a formal way. And in mathematics, you know, again, there might be things going on. Okay, at the level, here's a possibility, okay? You look at all formalized mathematics, and you say right now, the only thing I care about is the continuum limit, I care about Pythagoras' theorem, I care about, you know, Euclidean axioms, et cetera, et cetera, et cetera. But actually, somewhere deep in the automated theorem proving of, let's say, the Boolean algebra proof, there is some interesting general principle.
Right.
That is a completely different and bizarre general principle, unlike anything we've seen. Same thing might be happening in machine learning. There may be things that machine learning systems are implicitly discovering that should be a new area of science.
Stephen, do you think that in some way meta modeling or the extraction of, you know, non-trivial computational content from models, you think it can help in this regard? You know what I mean?
Interesting question. Yeah,
like,
I mean,
like what you were just saying, you know, especially like, let's say you're performing some computationally irreducible work and you come up with some finding. Great. But as you're saying, it's probably insufficient just to have, you know,
well,
tools
right.
and instruments
You're asking for an extreme form of meta modeling in which you take something which looked computationally irreducible and you say, actually, there is a reducible type model that can be applied to this thing. I mean, in that sense, so you're saying, you know, the usual idea of meta modeling, and when I say usual, meta modeling as a term is only a couple of months old. So, but I mean, you know, the usual idea is you take some messy model that somebody described in some paper that has complexity in its description. You know, some model that's about, you know, the I don't know, the leadership of in flocks of sheep or something, and you know that model has something about how the sheep looks around it and decides whether something or other about some other sheep, et cetera, et cetera, et cetera. And then the question is, what you observe. Let's imagine that the result of what you observe there is very complicated behavior for the sheep. Then the question is, what is the essence of what leads to that complicated behavior? Does it matter that the sheep has 4 legs and things like this, which might be in the model somehow? And you know, can we extract the essence of the model for the abstract sheep that has an unknown number of legs and other features that don't have to be sheep specific.
Right, and that sounds amusing, but ultimately the result could be, not having a 25 parameter model for sheep.
Yeah, right. It could be having something which is a generic model that has the feature that in this generic model the thing always becomes a single flock of sheep or something, and that's a generic result. I mean, this was a key question, in the epidemiology of this in this pandemic, was, as you change the possible models, when you have models for transmission, as you change the possible models, do you get robust results or not? If you go through the space of models, do you get robust results? And the answer was mostly no, which is why it was hard to predict a bunch of things. But I mean, so what you're saying is, what I'm imagining meta-modeling is mostly about is removing the fluff from models, removing tons of details about, was this sneeze spherical or was it whatever? And it, in the end, there's an essence of what's going on where it doesn't really matter. But now what you're saying is there a way to take some computationally irreducible result and take a set of those computationally irreducible results, for example? And I mean, that's a more difficult form of meta-modeling, because I think most of meta-modeling, as we're now describing it, is getting rid of human-generated complexity of people describing models in a more complicated way than is needed. This is different. This is a more intrinsic complexity, and it's not so obvious you can get rid of that. I mean, that in a sense, what you're asking for there is the essence of science. I mean, science is about going from the observed world, which is full of computational irreducibility, to something where we can tell a human story about what's going on. And and what you're asking is, in the usual way we do that is we tell certain kinds of stories that are based on our particular sensory data, et cetera, et cetera, et cetera. The question is, are there different kinds of reducible stories that can be told about the world? To which the answer, I suspect, is definitely yes. But okay, so then the next question is, what is the topology of that space? That is it true that we can get from our descriptions of the world today to those alien descriptions of the world, and we can continuously deform from our current descriptions to the alien descriptions? Or does that space have holes in it? And do we end up having to make some big sort of jump? I think that's the story of paradigm shifts.
Well, there might be some holes, but then the question is, are there still some nice, if we're able to find a way to navigate this kind of
right, but I think that's
space.
My guess is that's the story of paradigm shifts. That's why that happens. That's why, because this space is not a continuously deformable space, that's why you end up having to, I mean, anecdotally, the reason that the space, if you could always get, if science was always incrementally doable, that will be the statement that the space doesn't really have holes in it. It's always incremental. Incremental science will always work. In a sense, to prove that there are holes in that space is to prove that, incremental science will never get you to the end. In other words, it's kind of an interesting, it's a proof that current models of institutional science can't work, which is kind of an amusing claim. I mean, in other words, could you prove that by incremental progress, you essentially can never get, or it would take you 300 years by incremental progress to get there, but if you make this jump, you can get there in 5 years.
But what exactly would that jump really involve?
I think it's a different description language. I mean, in other words,
well, yeah, okay.
you've got some, which is to say, okay, let's talk about it in terms of mathematics. Okay, there is a way of abstracting from the microscopic level of an axiomatic structure generated by an automated, by a math formalization system, abstracting from that the Pythagorean theorem that you'd actually want to write down, which isn't the one that's in that system. The one that's in that system is probably full of all kinds of crazy stuff about that goes right down to the atomic level of the axioms. but there's a level of the Pythagorean theorem that's worth human communication. So the issue is, are there other things that are worth human communication that that extract different pieces, different results from that atomic level? That's the challenge. And the challenge is, but we don't really understand the transformation from the atomic level to the Pythagorean level, so to speak.
Well, that's what we're doing with this project.
Yes, that's the goal there. All right, let's look at. Unfortunately, we really need to talk about Troughs for a moment. And I'm supposed to go to a completely different meeting, but I'm having too much fun here. Let's see. Continuum limit, says Richard. I think aspects of the analytic continuation hyperoperation sequence. Iterates may be integer, real, or complex order. Don't completely understand, although that sounds like an interesting direction. Flows. What is Schroeder's equation? I don't know what that is. Topological conjugacy equation, which turns up in fractional function composition. Oh gosh, that's a whole nother can of worms. Yeah, I mean, I was going to, like a year ago, I was going to try and write something about fractional everything, fractional dimension, fractional function composition. I don't understand fractional function composition. If Richard understands that, I'd be interested to know about that. Oh, Schroeder's equation. Yeah, I know what you're talking about there. Yes, that's an interesting topic. Let's not go into that right now. Let's see. Different axiom systems, says Richard, are equivalents because they can be transformed to a central node, which for us is a geometric formulation. Perhaps. Theorem to theorem transformation. Diffeomorphic transformations for theorems must exist as structure preserving transformation or property preserving. Yeah, I mean, that's this question, right, of whether we can do, to what extent we can put geometry on top of this. Let's see. Okay, somebody comments that the Lindenbaum-Tarski algebra is related to this. I do not know what that is. Let's find out. I mean, Tarski's theory of truth is slightly related to this, although I'm skeptical about it. Oh my gosh, there's a thing. I've never heard of this. Okay.
What, Lindenbaum-Tarski?
Yeah, I don't know what that is. Okay, let's just take a look. System equivalence class of sentences for the theory. Provably equivalent. Oh, yeah, okay, I understand what this means. Huh. Yes, this is very relevant. Thank you. Yes, thank you. We will look at that more. That's very relevant. Let's see. Different mathematicians, says Richard, rely on principle of computational equivalence. Since we're self-modifying programs, we're already super Turing. I'm not convinced about that. Richard is commenting on Harvard Siegelman. Gosh, I haven't heard from her in ages. A picture of hypercomputation. I haven't heard from her in ages. I don't know what she's been up to. Let's see. Mark is asking, do we know about Richard Borchard's YouTube channel? No doubt it's interesting. Yeah, I mean, I certainly know of the person. I do not know the person myself. Richard is commenting on the fractional rule application, which I also want to look at. Let's see various other comments here. Let's take a look. Okay, Mark is saying it's like harmonic entropy, the human perception of rational ratios across 0-1 interval, where the ratios are not set up continuously but are perceived as such. Well, this is great. You guys are telling us about all kinds of things we never heard of. Okay, I'm going to put down my this is a things to look up.
Yeah, I'll make a little notebook of these comments.
Right. This Lindenbaum-Tarski algebra does seem highly relevant, and I'm certainly aware of Tarski's theory of truth, although I've never been a big fan. Also, I want to the Schroeder's the fractional application business is of interest also. Let me see. What is harmonic entropy? Let me just look at that. What on earth is this? I do not know about this at all. It's about perception of pitch. I don't know how that works. I don't know. I mean, I've thought about the theory of pitch perception and why some intervals are pleasanter than others and so on. Let's see. We should look at that. I don't know about it. Limiting object exists in an abstract sense, as in the Zeno effect mentioned earlier. And yes, calculus is a cognitive toolkit to help explore the consequences, says Richard. Yeah, AK is commenting calculus as the part of the electromagnetic spectrum that we humans can actually observe. Mark, gliders and wave packets in quantum mechanics. Yes, I think there is. There is, but it's much more complicated in hypergraphs, and we don't understand it yet. And that's something we really want to study, is the sort of topological obstructions in hypergraph rewriting. Okay, Richard is commenting on a tweet he has. That sounds interesting, but it's going to get us totally off track if we follow that. Okay. Comments that Nick Baer gave a lecture on heighting algebras. We certainly know Nick Baer, although he is doing a bunch of interesting work on graph rewriting, and there's a active project to try and understand the correspondence between some of that work and what we're doing. Okay, well, things to look at there. All right, I am supposed to go to a different meeting, but I just want to
Troughs?
Yes, I just want to at least define the what needs to be done there. Let me just see what I'm. Oh my gosh, I'm supposed to be dealing with. I have a day job, and it involves getting version 13 of Wolfram language out, which is very close. And I will have to go back and do some day job things in just a minute here. Okay, I just wanted to define this. And I'm sorry, we went way off track here, although this was interesting. The basic issue is we want, instead of using sort of a list of elements, we are imagining that our raw material is expressions, and then we are writing down the laws of inference in terms of operations on those expressions. And Nick has written exactly that. He's written substitution lemmas and critical pair lemmas as things that eat expressions. Is that a fair statement, Nick?
Yeah, exactly.
And I think we need to understand exactly how they eat, and they eat expressions, and the expressions they eat only when they have two-way rules in them, or at least one-way rules in them, can a substitution lemma operate. The TWR2 has to contain a two-way rule. Is that a correct statement?
Yes, that's what.
But element 1 does not have to contain a two-way rule. In other words, you can apply a substitution lemma to an expression that doesn't have as its top level node a this, right? So I mean, if we take this, for example, I mean, this thing is ultimately, I don't know whether this will look sensible or for it be craziness.
It's going to be blanks. Yeah.
It's too messy. Okay, so we need a decent version of that is a tree visualizer from these things. But the basic point is that we're going to be taking this, and your substitution lemma is going to take something like this. Like if we take this and we apply it to itself for the substitution lemma, that would work, right? We can just take, do you have like a trivial substitution lemma? I really want to go through this stuff. We need to.
Well, the code is like in another file.
Okay, all right. I think we probably should not do this now. And I know it's late in your day, Nick, and because we're very hot on this stuff, we're probably going to continue. Unfortunately, not live streaming, but we'll maybe continue in on the order of I can't do my arithmetic, 7 or 8 hours, which is unfair to Nick because that doesn't give him. I think we have to wrap up here, even though this is, and I think we need to. If people are really into it, we probably could live stream this later. This is. I think this is going very well. I think we're going to be able to figure out a whole bunch of stuff here. And really the next step, to my mind, there are 2 next steps. One is understanding troughs and understanding the analog of what we've done over here for troughs, which I think is going to look very similar. I think the one difference is going to be the injection of operators that, in a sense, we'll just have to say, these are the operators. This is the syntax with these operators, and this is the universe in which we're operating. And that will be sort of a human contributed thing. That's point 1. Point 2, I think that I really want to see, and I think, Nick, you seem to have some understanding of this from MetaMath and Lean and so on, what the actual, how we get, okay, do you believe that we can take theorems from MetaMath and just represent them as these kinds of correspondences? Is that a thing? I mean, that's what.
It's pretty cool, yeah. Without
Okay.
critical dilemmas, just the pure substitutions, and no trees as output, but just sequence of variables and constants. Yeah, but pretty cool.
Okay. But then what we'll see is the proofs in MetaMath will correspond to paths in the token event graph, and the tokens will be theorems in MetaMath. And then what I want to see is how those theorems knit together to form where I think it's going to be the case that all the bound variables have to be distinct. How those knit together to make the hypergraph that represents the state of mathematics as it is today. And then what we have to do is coarse grain that hypergraph to see, beyond the level of the microscopic elements, what is the math people care about level. We're getting there. This is we're going to figure this out, and it's and I think we're going to discover that math, it's not very surprising, that math is a human activity in the same way that physics is, and that the statement, it's fascinating that these statements that, for example, I made the statement for a long time, the math that we do is a consequence of sort of the history of the math that's been done. And I think that statement is probably not quite correct. The correct version of that is it's a consequence more of the math that's readily accessible from us given our sort of human characteristics. Anyway, more to work out. Let me just see these last comments and then we really have to wrap up here. Richard is commenting, lecture given in Edinburgh, categories, logic, and physics. That sounds like our kind of thing. Somebody from our team should give a talk there. Richard offering to ping a notebook which shows an instance of Schroeder using Kalman matrices. Oh yeah, it sounds interesting. It sounds interesting. Don't know about it. It sounds interesting. Computation tree logic is a branching time logic. By the way, I think Richard was the person who originally introduced us to the MetaMath system and team. So thank you for that. Computation tree logic is a branching time logic, meaning that its model of time is a tree-like structure. Okay, there's another thing I don't know about. I mean, this sounds like it sounds very multi-way. And it's gosh, there's so many things one doesn't know about. Okay. Oh, I see. Okay, I understand what this is. Oh, that's interesting. So this is something relevant to our attempt to ask something we're not asking today, which is, what is the distributed computing observer like? Which is a topic for another day. All right, we should wrap up here. Thanks, Nick and James. And I noticed computation tree logic was Edmund Clark was the person. Okay, interesting. Thank you to folks on the live stream. Many interesting comments and suggestions. Much appreciated. To be continued. All right, I need to disappear now. So bye for now.